All right, cool. Hello, everybody. Welcome to an unusual class today. So first of all, tried figuring out the whole recording situation. Was more difficult than I thought it was going to be. I found a way to do it. I just can't get my face involved. We'll see how that works. Hopefully that's not too bad. On top of that, I've prepared notes for this weird online class thing. They're long. They're very long. And I don't know how long this video is going to be. You guys obviously are clicking on the video. You saw how long this video is going to take. I don't know yet. It might be a 2.5 hour video. It might be very long. I hope that doesn't make anybody panic. Let me explain why the length. So the topic we're going to talk a lot about today is rational functions. And rational functions are a relatively deep and can be a tricky topic. And, just over the people of my class, some people are really keeping up. Some people are, struggling with a lot of the different concepts. And my thoughts are this video is going to go into detail in case anybody wants detail. If you are understanding a topic that I'm going into further detail about, you can skip those parts. Absolutely. If somebody is watching this video and it is a 2.5 hour long video, and you are somebody that's really keeping up, you can probably watch it in only 30 minutes. I don't think that you need to watch all of this. If I'm going into detail about a topic that you understand, feel free to skip it, skip the video, just skip the parts and record, and don't have to take notes. You can even speed up the video. So, I hope if this is a long video, it doesn't make anybody panic. So with that being said, let's jump into it. Last class, where we left off is we talked about end behaviors of polynomials. Now, all things considered, these weren't too bad, because end behaviors of a polynomial are basically as, x gets larger and larger and larger, as x goes to infinity, the polynomial is either going to infinity itself or the polynomial is going to negative infinity. So it's nothing too bad. And I hinted at last class that there are definitely examples of where it doesn't go to positive or negative infinity. They're just not polynomials. They're rational functions. And that's what we're going to talk about today. And to start, I'm going to go over a rational function review. We have gone over this several times, especially when we were doing domain and range problems. So if you feel like you have a good grasp of rational functions and what they are, this is a great part to skip. But if you wanted extra time looking at it, maybe this is a good time to, take it slowly and look through it. So let's do that. Rational function review. And again, if you don't need the review, definitely skip. So in short, a quick definition is a rational function is a function that can be represented as a fraction where the numerator is a polynomial and the denominator is a polynomial. So let me write that down. In short, a rational function is a function that can be represented, and I'm going to go over why I'm saying the word can, another spot that you can feel free to skip, but I am going to talk about why I'm saying can instead of has to be, is a function that can be represented as the quotient, or just a fraction, of two polynomials. Polynomials can be the same or different. If they're the same, the function is just one. So that's actually a boring example. So let's assume really that the two functions are different. Now, even if you're okay, now I'm at that part, you can skip the following part, because what I'm really going to do is I'm going to say it formally. I'm going to say it in a very, very formal, strict way. Formally, a rational function is defined as follows. So we're going to need some stuff. This definition is very algebraic. There's a lot of letters and no numbers. So if that's going to scare you, we're going to go over examples. It'll be fine. okay? So, but to start, we're going to need some stuff. So, to start, we need the degrees of the top and the bottom. If you remember what degree is, you're off to a good start. So, let little m and little n be natural numbers. And again, natural numbers are just counting numbers. And I'll put that in blue. So like 0, 1, 2, 3, ... Something. The n and m are one of those numbers. They can be anything. Now we need a lot. We need n numbers and we need m numbers as well. Or n plus 1 and m plus 1, actually, because, so we're going to let a sub 0, a sub 1, a sub 2, all the way up to a sub n, for whatever n is, be any numbers. They can be 0, they can be 1, they can be 10 million, they can be pi, they can be pi squared, so on and so forth. Be any numbers, except the one condition I'm going to put is as long as a sub n is non-zero. Because if a sub n was 0, then we don't care about that. And what we really care about is we'll care about the an minus 1. And the degree wouldn't be n, it'd be n minus 1. Or something lower. So I'm not saying this because it's a problem if an is 0. It's just, we're talking about a different case then. I'm only saying this so we know we're on the same page. That's all. Similarly, I need the numbers for the denominator. These are going to be the numbers for the numerator upstairs. Let's let these numbers be denominators. So let b0, b1, b2, ... bm be any numbers. And again, same idea as long as bm is non-zero. Again, nothing wrong if it is. It's just that's not the case we're talking about. Then the function, I'll call it q of x for quotient, is a rational function if it can be, and again, I'm going to go over why I'm saying can. Quickly, there's not like a long explanation, it's a quick explanation. Can be expressed as the following. This big conglomerate, I'm going to use 2 lines for this. Q of x is equal to, we have an times x to the n plus an minus 1 times x to the n minus 1 plus ... plus a2x squared plus a1x plus a0. So that's my numerator, and that is if you have a good grasp of what the definition of a polynomial is. You saw that that was what we defined a polynomial to be last class. And downstairs, we'll have all these b's. b2x squared plus b1x to the 1, if you would rather, plus b naught. So, before we move on, let's talk about what I mean when I say can. It can be represented. And the best way to do that, in my opinion, is just to look at a quick example. So we're going to just to create an example, let m equal 1 and n equal 2. So the degree of the upstairs is 2, degree downstairs is just 1. So we're going to let a2 be equal to 1, a1 equals 0, a0 equal to -1, b1 equal 2, and b0 equal -10. Just as a quick example. Then we're going to get the following. If I'm just going to plug all like this m into this m, this n into this n, a2 into a2, a0 into a0, and so on and so forth with these guys, then what I'm going to get is, I'll call it q of x as well. I'll get q of x is equal to, I'll also use 2 lines here, just to make the fractions not so small. Then what we'll get is, we're going to get 1 times x squared, because a2 is 1, plus 0 times x to the 1, because a1 is 0 rather, minus 1, because a0 is -1, under the same idea, we're going to get 2x minus 10 downstairs. And this is going to be equal to x squared minus 1 over 2x minus 10. So in this example, that is what our function is. X squared minus 1. Oops, sorry about that. X squared minus 1 over 2x minus 10. Now, how I could represent this fraction, if all of you kind of were keeping up with what I went over the first week with when I went over fraction rules, this is the same as saying I can split this guy into 2x minus 10 dividing 1 times x squared minus 1 over 1. Now, anything divided by 1 is just itself. So this is the same as 1 over 2x minus 10 times x squared minus 1. Now, this, in and of itself, this doesn't look like the form I wrote here. This is just one fraction. This is a fraction times a polynomial. It doesn't look like it per se. But because equals equals, I can write this guy as this form. So a function is a rational function if I can reduce it to this form. It can look like this, but if I can algebraically make it look like this, it's still a rational function. Now, just further examples and this is just more for fun than anything else. I'm just going to have fun with it. We're going to do a quick silly example is what I'm going to call it. Just to kind of point out things that you might notice. Again, this is very skippable, but I think it's fun to look at. So let's let m equal 0 and b naught equal 1 for the following two examples. A, we'll have n equals 2, and then we'll do, just to make it easy, a2 equal a1 equal a0 equal 1. So they're all just 1. It's just a quick way to write that. Then what we'll get is that our q of x, or whatever you want to call it, f of x, g of x, whatever. I'm just doing q for quotient. Then what we'll get is, after doing all the math, x squared plus x plus 1 all over just 1. Or x squared plus x plus 1. And you might say, that's just a polynomial. And you'd be right. And this isn't a proof by any means, but this is just a quick example showing that all polynomials are rational functions. Because I can just take this bottom part to literally just be 1, and then I have a polynomial divided by 1, or just the polynomial itself. So showing that all polynomials are rational functions, but, as we'll see later on, not all rational functions are polynomials. And taking it even a step further, in the next example, we'll let n equal 0 and a0 equal 5, for example. Then we're going to get q of x is literally just equal to 5 divided by 1, or just 5. A constant function, showing also that constant functions are also rational functions. So by no means is this a proof. These are just examples, but they're intuitions showing that polynomials are rational functions, constants are rational functions. Cool. And at any point, feel free to pause and whatever. All right, so now we're going to talk about the next idea. Now that we've kind of gone over quickly rational functions, examining and behaviors of rational functions. Because this is where things will get interesting. And we're going to have some fun with it. So last class, I briefly kind of hinted at that, all the polynomials we were doing had, as x goes to infinity, as I was saying earlier, x goes to infinity, the polynomial p of x, let's say, was going to plus minus infinity, one of those, always. And I was like, do you think this will always happen? And the reality is it won't always happen. If I take, for example, f of x is equal to 1 over x. That's a great example. It's a tricky one, so we're going to talk about it later. To start, I'm actually going to do a simpler function. So this is our main idea here. and we'll talk about it, but I'm actually going to start with an example on this guy. And we're going to start with something that doesn't look easier than 1 over x, but actually is. Let me move this down. So I'll have g of x. That's a horrible g. Sorry if my handwriting's bad at all. G of x is equal to 1 over x squared, which might not look like it's easier to deal with than 1 over x, but to an extent here, it is easier. And if you're joining me from the rational expression review, this is a rational expression where n equals 0, m equals 2, a naught, or a sub 0. It's very common in math to call anything sub 0 naught. I don't know why. So a sub 0 is the same as a naught. If you hear me, I'm only pointing that out in case you hear me say it and go, what is he saying? A naught is 1, B2 is 1, and then B1, B naught are both 0. Plugging those in to this idea, you get 1 over x squared. Oops, sorry about that. So let's talk about this. And when we talk about M behaviors, the way we talk about M behaviors is we talk about what happens as x gets really large or really negative. Let's start with as x goes to infinity, positive infinity. And I think, like I was hinting at last class, these ideas are really the beginning of limit problems, which you'll deal with if any of you are taking Calc 1. And if any of you are taking math any further, limits never go away. They're very important. Now, one of the best ways to discuss limits, in my opinion, especially on the real numbers, is powers of 10. So we're going to talk about what happens when x equals 1, x equals 10, and then we can do when x equals 100, but we're going to skip to 1,000 just so you guys get the picture. So what happens in these moments? Well, when x equals 1, what we're going to get is g of x is equal to g of 1, because x is 1, is equal to 1 over 1 squared, or just 1. That one's a simple one. In the next case, we'll get g of x is equal to g of 10, because again, x is 10 in this case. And then what we'll get is we'll get 1 over 10 squared, or 1 over 100. And immediately we're dropping. We went from 1 to 1 over 100 as we went from 1 to 10. But 2 is not a pattern. So in this case, when x is 1,000, we'll get g of 1,000 is equal to 1 over 1,000 squared. And all that's going to be is 1 over 1 with 6 zeros behind it. 3, 4, 5, 6. 1 over 1,000,000. So as you can see, if this process were to continue, as x gets larger, the function is by no means getting larger. In fact, as x goes to infinity, it would appear g of x is going to 0, actually. Which is rather interesting. And similarly, because this guy, let me just read my notes real quick. I see. My fault. So, similarly, I'll let you guys check it for yourself. As x goes to infinity, g of x is also going to 0. Just do these same processes. When you plug in 1, you'll get 1 over negative 1 squared, which is the same as 1. If you want to plug in x equals negative 10, you'll get 1 over negative 10 squared, which would be 1 over 100. You'll get the same values. So hopefully this is believable that as x goes to infinity, negative infinity, g of x goes to 0. And what I have prepared is I have a Desmos available, which is an extremely useful tool that if you've shown up to class a lot, you've definitely seen me use several times. And I've got a couple functions prepared for this class. And so this first guy is 1 over x squared. And as you see, if I can like pinch this thing, so if I pinch this thing and really look at what happens as x get larger and larger, you see it's not actually crossing 0 at all. And if we were to zoom in really, really far, it'll take a long time. But if we were to zoom in really, really far, we would definitely see, this application, sorry, work with me a little bit here. Sorry, this application can be a little spotty when I'm trying to zoom in and out. All right, that's not working with me the way I wanted it to. If you were to zoom in really far, you would, there we go. If you were to zoom in really far, you would see that it gets actually closer and closer to 0, but it's never actually gonna hit 0. It's just getting closer and closer as x gets larger and larger, or as x gets more and more negative. But as you kind of saw in that image that I was doing, and I'm actually gonna go over here to this guy, because this is just the drawing of 1 over x squared, my drawing of it. So as you can see, as we just discussed, there's this line at y equals 0 that the function will never cross. It's not a line that's actually drawn. It's this invisible barrier that will physically not allow the function to drop further than here. It's this invisible line. Excuse me. And as you can tell, that's not the only line that's happening. In the function on Desmos, if we were to do the opposite and have this thing, come on, work with me. It was working with me right before I started recording, I swear. All right, it's not working the way I was hoping it would. It never works when you need it to work. Okay. Well, regardless, I think it's believable. I was trying to make it so that as I'm scrolling up, the numbers are going up quicker. But you can believe me that this line these lines will never actually touch. They're going to get closer and closer and closer as the numbers get larger and larger, but they never actually will touch. So again, there's also this barrier blocking the lines from touching there. So we have a barrier there and we have a barrier there. These barriers are called asymptotes. They have a very special name that I know a few of you have discussed before. But so in this function, there's something important to notice. If I were to plug in x equals 0 into g, we're going to get g of 0 is equal to 1 over 0 squared, or just 1 over 0. And as we know, this is definitely undefined. You can never have a 0 in the denominator. So we can't plug in 0 into g. However, based off of how we've kind of been discussing things as x gets larger and larger and larger, but never getting to infinity, in a similar way, we can discuss what is the behavior of g, what is g doing, as x approaches 0. So let's do the same thing we were doing here, but instead of making x larger and larger, let's make it smaller and smaller. So again, we can discuss at x equals 1, we already did this one, g of x will be 1 over 1 squared, or just 1. What if I go in the other direction and say x is 1 over 10? Well, g of 1 over 10, well, that'll be 1 over 10 squared, which is the same as, again, if you were paying attention in the first week when we went over fractions, exponents, all that fun stuff. This will be the same as 1 squared, sorry, I'm trying to fit it all here. 1 squared over 10 squared, or just 1 over 100. And by keep, change, flip, this will be 100. And again, we can go straight to, right. This is why I write down the notes before I actually am going. There's something I want to point out. What happens if x is equal to negative 1 over 10? Well, g of negative 1 over 10 will be 1 over negative 1 over 10 all squared. Well, what's going to happen there is anytime a negative gets squared, it becomes positive. And we'll get back to our situation right above, 1 over 100. These are the same. And we can conclude that this is 100. In fact, if you remember a definition I went over before, let me write this in a different color because you don't need this right now. But if you are really keeping up and really enjoying the course, in fact, nope, sorry, not f, g, that's the function we're working with, is an even function. And that's actually why I was kind of saying g of x squared is a nice example here. Since it's an even function, g of x will always be equal to g of negative x. That will always be the case. So let's continue the process. X equals 1 over 100, let's do. Then g of 1 over 100 will be 1 over 100 squared, which will be the same as just 100 squared, or 10,000. And again, based on what's written in blue, if I had x is equal to negative 100, 1 over 100 rather, g of negative 1 over 100, well, because it's an even function, the negative is the same as the positive when I plug it in. This is the same as g of 1 over 100, which we just found is 10,000. So regardless of whether we're talking about positives or negatives, as x gets closer and closer to 0, whether it be smaller from positive numbers or getting less negative, as x approaches 0, it would appear that these numbers are getting larger and larger. I could do 1 over 1,000, and I would get 1 with 6 zeros behind it. A million. 1 over 1,000 would be a million. And similarly, negative 1 over 1,000 would also be positive a million. So it appears, if I were to continue this process, as x gets closer to 0, g of x is going to infinity. It's getting larger and larger. There's no bound. So the closer x gets to 0, the function blows up, which is kind of what's happening here. As we were getting closer and closer to 0 here, I'm really still trying to get this thing to work out. As we get closer and closer to 0, the function blows up in value. It gets larger and larger by a lot. Yes, I am still trying. This is really annoying. It was working perfectly right before I started recording, which is so wonderful. And now it's just not working the way I want it to anymore. But still a useful tool. And we will probably still go back to it anyways. So, as x goes to 0, g of x goes to infinity. This brings me to the term I was alluding to earlier, with these barriers. These barriers are called asymptotes. There are two kinds, one that's a vertical asymptote and one that's a horizontal asymptote. We will discuss them both because they're actually both interesting, both have similar names, both have similar ideas, different ways of finding both. They behave pretty differently. So definition, that's my usual, I do def in a box. I'm getting this straight from the textbook, by the way. A horizontal asymptote, apologies. Sorry, my Apple Pencil's starting to die on me a bit. Been using it for over a year at this point. A horizontal asymptote of a graph, and again, these asymptotes are these invisible lines. So we can think about them, if we want to look at them, we don't want them to be invisible anymore. So we want to think about them as a line, and we've discussed lines. And specifically, if you guys are really keeping up and remembering, of a graph is a horizontal line. And horizontal lines all have the same form. They're all just a constant function. Is a horizontal line, y equals b for some b value, where as x goes to infinity or x goes to negative infinity, either way, f of x is going to be. Not equal to b, sorry. It's approaching b. And again, that's actually, I'm glad I almost made that mistake because these are not equal signs. They are infinitely approaching. That's the idea. As x gets larger and larger and larger, f of x is getting closer and closer to b. But I'm not saying x is infinity, then f of x is b. What I'm saying is as x gets larger and larger, f of x gets closer and closer. Or as x gets more and more negative, f of x gets closer and closer to b. Now, believe it or not, we actually are not quite ready to discuss a vertical asymptote. We're only ready to talk about a horizontal. We need one more thing before we can discuss how to deal with vertical asymptotes. And the best way, I think, to kind of uncover why it's necessary, and I always say this, mathematicians never choose what is right, we listen to what is right. So we never add issues if we don't have to. So I just want to examine, or I want to display why we need to add further notation. And the best example to do that is, let's examine f of x is equal to 1 over x. And to hint at the problem with this guy is not an even function. So things will fall apart and things will be actually very different. And I'll let you guys do this part. One can show. The horizontal asymptotes are the same. As x goes to, rather, let's write it like this. As x goes to infinity, f of x is going to 0. And as x is going to negative infinity, f of x is also going to 0. We can show that. But that's not what's interesting about this problem. What I would much rather do is, under the same idea as the last problem, so we're going to do the same thing as, sorry, I worded this wrong. Under the same idea as the last problem, let's see what happens as x gets closer and closer to 0. So, well, I could start in the case where x equals 1, and then we get smaller, but let's just jump right ahead into 1 over 10. Well, then, if you're good with your keep, change, flip, f of x is going to be 1 over 10, which is just 10. I'll let you figure out the details there of the keep, change, flip. But if x is negative 1 over 10, then f of x is going to be 1 over negative 1 over 10, or keep, change, flip, negative 10. Similarly, let's do 1 over 100, positive and negative. Then f of, I called those x. Oh, that wasn't really wrong, but I probably should. I don't want to confuse people. This is f of 1 over 10, negative 1 over 10. It's going to be f of 1 over 100. Well, it's going to be 1 over 100, or just 100. And similarly, if we have x is equal to negative 1 over 100, then f of negative 1 over 100, well, keep, change, flip, that's going to be negative 100. So if you're really keeping up, you could probably spot what the problem here is. The problem here is, I'll write it in quotes, as, because this isn't technically true, and just showing why we need to add further detail to really communicate what we want to communicate. As x goes to 0, f of x is going to positive infinity, and f of x is going to negative infinity. So this is very confusing. This is a problem. We don't want this. We want it very clear. As x is going here, x is going here. Not here and here. That makes no sense. So we need to be a little bit more specific in what's happening. So one thing I want to point out, let's go over to Desmos. And let's get rid of that function and look at 1 over x. So again, 1 over x squared is this purple line. And I'm going to try and figure out this thing once again. And it's not working. Okay, well, I guess we just got to zoom in. It's never doing what I want it to do, and it's looking really unfortunate. It is what it is, and I'm going to keep trying. Anyways, so this is what the purple 1 over x squared looks like. 1 over x looks very similar, except it's flipped on the negative side of things. It's underneath. So if you kind of think about it, as we're approaching it from the right, let's just look at the right. As we're going to 0 from the positive side, it's going up and up and up. It's blowing up. It's exploding in value. But if I were to look just here, as we get closer and closer to 0, it's getting more and more negative. So it would appear the way to write this is the following. So the less confusing way, let me put this in a different color so that we know that this is bad. Let's put this in red. So we know that that's a bad thing. Instead, what we'll do is we'll say the following. So we will say that as x approaches 0, from the right, left and rights are important here. As x approaches 0 from the right, f of x is going to infinity. But as x approaches 0 from the left side, f of x is going to negative infinity. And I want to be clear about something for a second. Some of you might be thinking, oh, what about if I view it as from the positive or the negative side? Well, the reason I don't want you thinking about it like that is let's look at this third example, 1 over x minus 5. In this example, as you can see, a lot of these x values here are positive. We have 2, 4, 3, 1, and so on and so forth. And those are what's getting negative as well. So it's not about positive and negative. It really is about left and rights. As I come, in this example, as I come at it from the left, I am still trying. Every time I bring up this page, just assume I'm trying to figure this out. It just stopped working entirely the second I started recording. Maybe it is something to do with the recording. Anyways, as I'm coming from the left, it's approaching negative infinity. As I'm approaching it from the right, it's going to positive infinity. It's not necessarily just the negative values make it go to negative infinity. But this is annoying, and as I've hinted at to you guys before, mathematicians are lazy. So we don't want to write that every time. So there's a shorthand. Instead, what we'll write is x goes to 0 and put a little plus sign in the top right. What this means, in words, literally, as I were to read that sentence, that's saying x approaches 0 from the right. And similarly, oops, close the quotes. I'm going to put a negative sign in the upper right, meaning x approaches 0 from the left. And the only reason we do the plus and negative here is because in this form, the axes, the way we read axes, and again, if you're not a native English speaker, this may be weird for you, but in English, we always read left to right, as simple as that. Positives are on the right side of the axes, negatives are on the left side. Simple as that. So in a way, this means coming from the right side, coming from the left side, coming from the positive side, coming from the negative side. So my suggestion is, if that's weird to you, I would pause the video, digest it for a bit before moving on. Assuming you did that, now we are ready to discuss what a vertical asymptote is. We just needed these bits of notation first. What does it mean to have a plus sign in the upper right and a negative sign in the upper right? A vertical asymptote is a vertical line. Now again, this is a confusing topic. Horizontal lines are always y equals b. Vertical lines are always x equals b, or x equals k, for example, something like that. When it's x equals, it's a vertical line up and down. When it's y equals whatever, a constant, a number, we get a horizontal line. So, is a vertical line x equals a for some value a, such that as x approaches, negative a, or a from the left side, f of x is going to infinity. One of the infinities, plus or minus. I'm just going to write this plus or minus to indicate it could be positive, it could be negative, either way. And similarly, or x going to a from the right, then f of x also going to plus minus infinity. Now, despite needing the extra notation for what a vertical asymptote is, we've done basically how to find vertical asymptotes already. Because basically what the vertical asymptotes exist at are the exact points where x is not in the domain of the function. So let's do a quick example of that. So we got some function. I got this example from the textbook. They called it k of x, and because it's a rational, I'll write it over 2 lines. So we'll get 5 plus 2x squared over 2 minus x squared. That'll be our rational function. And we want to find the vertical asymptotes. Find vertical asymptotes. And again, all we're doing is finding the x values that make the denominator go to 0. We want to know exactly when that happens. That'll give us literally exactly where our vertical asymptotes are. And I even have this function prepared in Desmos, and we can examine it after we do the math. But again, all we're doing is solving this. What x values make this equation get killed, go to 0? Well, we can write this as, let's see, this will be 2 minus x, and that should be x plus 1, maybe? Let's do that out really quickly. Let's see if I did that right. This will be 2x plus 2 minus x squared minus x. Close, but not quite. We want this guy positive, this guy, or rather this guy negative, this guy positive. So how do I do that? I think I like that I'm doing this. You can do quadratic equation here. I also probably should have prepared. That's negative. What happens then? This goes to negative. Aha, I also will need this to be negative. So now let's try this again. So we're going to get negative 2 times x will be negative 2x. Negative 2 times negative 1 will be plus 2. Negative x times x will be negative x squared. Negative x times negative 1 will be positive x. And in fact, this is giving us what we want. This will be 2 minus x squared. Beautiful. And that is how I factor. Quadratic equation was probably even quicker than that. So we're getting that this guy can factor into these two terms. And as I've said, I've talked to you guys before about many times why we can now just split this. If you have any questions on that, feel free to ask. I always like going over that. Give myself a little bit more room. And the split into negative 2 minus x is equal to 0, and x minus 1 equals 0. Then we'll get negative 2 is equal to x, and x is equal to 1. Those are the values, when you plug these two into the denominator, those are the values that make it 0. So therefore, very simply, this must mean there are asymptotes, vertical asymptotes. At x equals negative 2 and x equals 1. Let's look. Let's see if we actually see that. Turn that off, turn this function on. Might have to zoom out a bit. Oh, because of the axes being screwed up. Oh, wait, I can manipulate the axes here, actually. How do I do that? What do I want? I want elongated x-axis. So let's go from like negative 1 to 1. And then we'll do. Well, actually, I want it a little bit bigger. Oh, look at that! Look at that! I fixed it. Beautiful. So you can see at x equals 1, this line right in the middle that I'm sliding along, you can see the functions on either side, up or down, do not hit the function at all at x equals 1. Similarly, x equals -2. It's like the function is avoiding these asymptotes like the plague. They refuse to ever touch them. So glad I figured that out. Cool, so hopefully that's relatively believable that those are the vertical asymptotes. Now, I want to pause really quickly to cough, but also the textbook discusses things called removable discontinuities. As far as I can tell, none of the homework questions have to do with it, none of the practice problems have to do with it, and hopefully nothing on the test will have to do with it. Considering that, it's also a relatively confusing topic. I'm going to skip it. If you are looking through the textbook, or if you do find a practice problem that you're confused about removable discontinuities or whatever, feel free to email me, ask me, come to my office hours. I will happily go over it. I just think it's slightly confusing, and I just don't want to further confuse people. So we're going to skip that just for now. Now, so that's how you find vertical asymptotes. I'm only going to do one example because we've already done a million of these before. What happens when the denominator is 0? Again, if you want to go over that, feel free to ask as well. So we're going to move on to horizontal asymptotes. Horizontal asymptotes are relatively difficult, but they're not too bad. They're just weird. And they depend entirely on the degrees of the top polynomial and the bottom polynomial. So because I don't want to rewrite this, I'm just going to grab this general form. Oh, let me also make clear. Finding horizontal asymptotes. So we'll start with this general example. Now, in this example, what I hinted at earlier is that the degree of upstairs of the numerator is n. We need that. And we will need the degree of the denominator, which is m. The degree of the numerator is n, and the degree downstairs denominator is m. There are three cases that can happen. Case 1, n is strictly less than m. Case 2, they're equal. You'll never guess what the third case is. N is greater than m. Oops, Jesus. Depending on what we get, depends on how we find horizontal asymptotes. Now, I'm going to explain what to do in each of these three cases, and then I'm going to go over examples of, I think, just the first two cases. Yeah, just the first two cases, because you'll see case 3, this case, we're not going to discuss, but we'll figure that out why. I'm going to give examples of these two cases of why it works the way it works. If you want to skip it, I get. If you only care about how to do it, not why it works, I get that. I do not recommend that, but I can't force you to do anything. So, excuse me, I got something really stuck in my throat. Sorry about that. So, in case 1, what do we do? Well, in case 1, what's happening is that the bottom is bottom heavy. It's way bigger than what's ever happening upstairs. And what that means is if n is less than m, then there's a horizontal asymptote at y equals 0. So, in the language we've been discussing, as x goes to infinity, Actually, as x goes to infinity, or negative infinity, yeah. So I'll just write that shorthanded. As x goes to plus or minus infinity, doesn't matter. Either way, then our function q of x goes to 0. No matter what, as long as n is less than m, the asymptote's at 0, always. This could be 5, this could be 10 million. Oh, whoops, 5, 10 million. It could be 1, could be 2, anything. And I'll go over an example why that's the case. Case 2. What happens here is if n is equal to m, then something weird happens. Then there's a horizontal asymptote at y is equal to a sub n divided by b sub m. And again, there will be an example that we'll go over that I think will actually really help show why that's the case. And again, that means as x goes to plus minus infinity, q of x approaches this a sub n over b sub m. And keep in mind, what those are is they're the leading terms. They are the coefficients in front of the variable with the highest exponent. The coefficient in front of the degree. That's a shorthand way to describe it. Case 3, we do not have a horizontal. We do not have a horizontal asymptote. We have a slanted asymptote, which is, all things considered, significantly more difficult to deal with. This is when the numerator is larger, when it's top heavy. All I'm going to say here, because all that's pertinent to the course, is if n is greater than m, then there is no horizontal asymptote. There is a homework question about that, actually. One of the homework questions is like, that gives you like options, horizontal asymptote here, 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 or it doesn't exist. And there is a solution where there is no horizontal asymptote, and it's when the numerator will be strictly greater than the denominator. We will not discuss much about this case, but there is stuff to be doing about it. But let's go over quick examples about why this is the case and why this is the case. So I'll skip a line, case 1 example. Let's go over a very exaggerated example. Let me skip more, and because it's a quotient, I'll use 2 lines. F of x is equal to x plus 1 over something way larger, x to the 10th. So, if you're really keeping up, so n equals 1, m equals 10. Degree upstairs is 1 because the exponent here is just 1, and the degree downstairs is 10 because the highest exponent is 10. The only exponent is 10. So let's look at what happens as x gets larger and larger. Excuse me, I've really got... Sorry about that. Hope that's not too annoying. So, I chose this as an exaggerated example for a reason, so you can see that it explodes really quickly. But this will happen even if the degrees are closer, like 1 and 2. When x equals 1, f of 1 is equal to 1 plus 1 over 1 to the 10th, or just 2 over 1, or just 2. If the next example is literally just 2, watch what happens. Then f of 2 will be, 2 plus 1, let's make that clear, over 2 to the 10th. So that'll be 3 over 1,024. Much smaller than 2. Let's make this even smaller. X equals 10. Then f of 10 will be 10 plus 1 over 10 to the 10, which is just 1 with 10 zeros behind it. So this will be 11 over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What is that? That'll be... Did I write it down anywhere? Nope, didn't write it down. So that's hundreds, thousands, millions, billions. 10 billion. 11 over 10 billion. So what I want to point out in an example that's really happening is as x gets larger, this x stops mattering at all. At all. This x to the 10th just dominates this guy. It makes it so this guy stops mattering at all. And I chose these numbers so that it's a little bit more obvious that I didn't have to go very far to show that there's a big dip. But even if it was just like x to the 1 plus 1 over x squared, let's say, instead of x to the 10, just x squared, this will happen anyways. Maybe not as quickly, not nearly as quickly, but x is going to infinity. At some point, this will happen, and the whole thing will just get significantly smaller and smaller. So that's why in this case, when n is less than m, the top just stops mattering at some point, depending on n and m. Again, in this example, I chose it so that very quickly that numerator stops mattering. But at some point, no matter what, it gets smaller and smaller. I hope that's a little clear as to why we do that. If the bottom is bigger, it's always going to 0. Case 2, I'll start a new page. Not that it's going to be that much room, but... Case 2 example. I'll do h of x, and again, it's a quotient, so I'll use 2 lines just to make it look a little neater. I know my handwriting is not great. Apologies for that. 4x cubed plus x over 2x cubed plus 1. Degree upstairs is just 3. Degree downstairs is 3. So this definitely fits into this case where the degrees agree on each other. Degree agree. That would be my rap name. Anyways. So let's do the same thing we have been doing. Let's look at what happens as x gets larger and larger. And I'll skip when x equals 1. Let's just jump right into x equals 10. Then h of 10 will be equal to... let's give myself a little bit more room. I did not plan this part too well. I'll just zoom in and try to be neat. Let's see how that goes. 4 times 10 cubed plus 10 all over 2 times 10 cubed plus 1. Hopefully that's, I don't think that's too bad. Which is equal to 4010 over 2001. And this will be roughly equal to, let's just approximate it, this will be equal to 2.003998. Let's make x larger. X is equal to 100. Then h of 100, well, this will be 4 times 100 cubed plus 100 all over 2 times 100 cubed plus 1. What this will be is it'll be some large number, 4,100,000 divided by, 2 million. Oh, let's do this right. So it's going to be 5 zeros. 1, 2. There we go. 2,000,001, which is approximately, I have this written down, 2.000049. It gets closer and closer to 0. And that is what we'll continue to, apologies. It gets closer and closer to 2. It's dropping and getting closer and closer. This process will continue, I guarantee it. What will happen is, as x goes to infinity, h of x is going to 2. But what is 2 in this case, really? 2 is equal to 4 over 2, which is absolutely our coefficients in front of the degrees, which is our a sub n over b sub n. So in this example, what I'm really trying to highlight is, in the last example, as x gets larger, the top stops mattering. In this example, as x gets larger, whatever is besides the leading term in the degree stops mattering. That's what stops mattering. Everything else, just all that will matter is the 4x cubed over 2x cubed as x gets larger and larger. And again, that was just an example as to hopefully illuminate why we have this. Let's do an example. We'll have f of x, sure, call it f. Will be 4x plus 2 divided by x squared plus 4x minus 5. Find asymptotes, horizontal and vertical. Let's do vertical first. Well, again, all we care about with the vertical asymptotes, when is the bottom going to be 0? All we care about. So that's exactly what we'll do. Set this guy equal to 0, solve for x. I'll do the double arrow to say this statement implies what it will ever be after the arrow. This is the same as saying, well, this is much easier to factor. This will be x plus 5, x minus 1 is equal to 0. Don't believe me, feel free to distribute for yourself and you'll see. And so now we can split this guy and we'll get x plus 5 equals 0 or x minus 1 equals 0. And in the end, concluding x equals negative 5 or x equals 1. Those are the situations that will make the bottom 0. And in fact, because of that, that is exactly our vertical asymptotes. Therefore, oh, I have not gone over that. These 3 dots just means therefore. That's all that means, but let me actually write that. Therefore, x equals negative 5 and x equals 1 are vertical asymptotes. Let's do horizontal. Well, horizontal is actually really easy in this problem. Because in this part, what we have is that, well, let's do the degrees. The degree of numerator is just 1, because we have 4x to the 1 plus 2, n equals 1. Degree of denominator is 2, because we have x squared, x to the 1, and then a constant term, so we'll get m is 2. So we're in a case where n is less than m. 1 is certainly less than 2. So because of that, what we're going to enact is we're going to do this rule. Well, if n is less than m, guess where the horizontal asymptote is? It's done. It's at y equals 0. So horizontal asymptote at y equals 0. Nice quick example. This is the point in the class where I would be like, any questions? But I'm talking to myself in a lonely room. Such is life. Anyways, let's do another example. I am definitely gaining a lot more respect for all the teachers who taught during COVID. This is very strange. But we're going to up the ante a little bit on this problem. We're not just going to find asymptotes. We'll do h of x for this guy. Just to make you guys more comfortable, you can call functions whatever you want. H of x is equal to 3x squared. Let's zoom in to try and make it nice. Plus 10x minus 25 all over 4x squared plus 21x plus 20. Find asymptotes But also, we're going to do a little bit more and find intercepts. There's a reason I'm doing this. Now remember, intercepts, as far as just defining what an intercept is, really isn't too bad. X-intercepts are the x values that make, or in this case, h of x. X values that make h of x 0. And the y-intercept is just what happens when when you plug in 0. What is h of 0? Simple as that. But there's a reason we're going to do it in this problem. Well, mostly just moving forward what my next topic will be. Anyways, so let's do this. So we'll do vertical asymptote first. Again, that is just whenever the bottom is 0. So we want to know, when is 4x squared plus 21x plus 20 equal to 0? For this guy, I'm probably going to do quadratic formula because this just seems like a nightmare. And hopefully it'll reduce nicely. I have no idea. That's a lie. I'm actually looking at the answer now. All right, that's not too bad. So we'll get, what is the quadratic formula? Hopefully we all know it. It'll be minus b plus minus square root. Just trying to fit it all in here. B squared minus 4ac all over, oops. Again, I need to get a new Apple Pencil. Over 2a. And again, this is our a in the polynomial. This is our b. This is our c. So we'll get negative 21 plus minus square root 21 squared minus 4 times 20. Might need a calculator for that one. All over 2 times 4. So this will be negative 21 plus minus square root 21 squared, 20 squared is 400. 21 times 20 is 420. And then another 21 would be 441. Let me just double check that. 21 times 21 will be 441. Cool. So this will be 441 minus 4 times 20 is 80. 80 times 4 will be 320. All over 8. 2 times 4. Negative 21 plus minus square root 441 minus 320. It's actually quite nice. It'd be 121. That is a perfect square. All over 8. So we're getting negative 21 plus minus 11 over 8. Now again, what does this plus minus mean? In the quadratic formula, plus minus just means that you're expecting 2 answers. One's when it's plus, one when it's minus. The only situations you get one answer is when whatever happens in this denominator is going to be 0. And then you'll get negative 21 in this case, plus minus 0. It's going to give you one answer. But in this case, we have plus minus 11. So we have vertical asymptotes at x equals negative 21 plus 11 over 8 and x equals negative 21 minus 11 over 8. Or x is equal to, that'll be negative 10 over 8 or negative 5 over 4. And x is equal to negative 21 minus 11 will be negative 32 divided by 8 will be negative 4. Are the vertical asymptotes. Cool. Vertical asymptote's done. Let's move on to the horizontal. Well, the degree upstairs is 2, and the degree downstairs is 2. We've got 3x squared, 4x squared. So what we do in that case is we just divide whatever numbers are in front of them. So therefore, If you want to be cool and mathy, this is the symbol for therefore, 3 dots in the shape of a triangle. Therefore, as x goes to plus minus infinity, whether it's going to plus infinity or minus infinity, you get to choose. Either way, it doesn't matter. H of x is approaching 3 divided by 4, or just 3/4. Or in other words, there's a horizontal asymptote. At y equals 3/4. Perfect. Now, moving forward, the reason I'm talking about we want to find intercepts is because moving forward, we want to be able to just draw rational functions given a list of criteria. That will be what our next example is. And one of the very helpful things are where the intercepts are. So I want to make sure we're all comfortable with where intercepts are. X-intercept. And again, these intercepts are just, x-intercept means where does the function cross the x-axis? Y-intercepts are where does the function cross the y-axis? Very often, especially in these examples, rational functions, we are expecting multiple answers for the x-intercept. We're expecting it to cross the x-axis multiple times, whereas the y-intercept will only ever be crossed once, exactly once. If it's crossed more than once, then it's not a function, because it fails the vertical line test at the y-axis. So here we might be expecting more than one answer. Let's see. Well, the x-intercept is just the same thing as solving what x values satisfy h of x equals 0. Or just plugging in what h of x is, the exact same question. What x values satisfy 3x squared plus 10x minus 25 over 4x squared plus 21x plus 20 is equal to 0. What x values satisfy that? Well, there's one nice thing that we can use here. Something I've talked about, but it's one of those fraction properties that I always write on the board very quickly that I went over in detail in the first 2 weeks. A little tricky to deal with, but hopefully not too bad. The property is if we have the situation where a over b is equal to 0, the only way a over b can be equal to 0 is if a is 0. Because the denominator of a fraction will never affect it being 0. The denominator can never be 0 to begin with. It'll never make or break the fraction being 0. What determines a fraction being 0 entirely is just what's happening upstairs. So if this whole fraction is equal to 0, the only way that can happen is if the top is equal to 0. And now we solve this. Again, I'm going to use the quadratic formula, where this is my A, this is my B, this is my C. How did I do the quadratic earlier? I kind of like to let's start a new line. So by quadratic formula, this means this will be x is equal to negative b plus minus square root b squared minus 4ac over 2a. I still don't know when I memorized that. I never used it when I was doing pre-calc. I would always, back then I was kind of silly. I would always try to factor it the way I was doing it earlier. And if I couldn't, I would just get more stubborn about it. I don't know when I memorized this, but it's in my brain somehow. So again, b is 10, so we'll get negative 10 plus minus square root b squared, which is 100, minus 4ac, which would be 4 times 3 times 25. Something seems wrong there. What am I doing wrong? It's negative 25, that's why. Because if it was positive 25, we would have gotten a negative underneath the radical, and I was screwing something up. negative 25. Apologies for that. All over 2a, or 2 times 3. So we're going to get negative 10 plus minus square root 100 minus... So 4 times 25, 4 times negative 25 will be negative 100. Times 3 will be negative 300. Minus minus will make it plus 300. All over 6. And these numbers are working out in our favor. This will be negative 10 plus minus square root of 400, or square root of 400 is 20 over 6. So we're getting x is equal to negative 10 plus 20 over 6, or x is equal to, actually I'm talking about asymptotes, so there'll be an asymptote at both of them, and x is equal to negative 10 minus 20 over 6. Or we'll get x is equal to 10 over 6, which can reduce to 5 over 3. We'll get negative 30 over 6, which reduces to just negative 5, actually. And those two are our... I actually totally forgot what we were doing here. We're not doing asymptotes. Apologies. But it is where it crosses the x-axis. Are our x-intercepts. Apologies. Sorry, I misspoke earlier. We were not doing asymptotes. These are x-intercepts. So the function crosses the x-axis exactly when x is 5/3 and when x is negative 5. Now, one thing I want to quickly point out is that these are the x values of the intercepts. If a lot of you have struggled with these on the homework. A lot of you have come up to me being like, I'm putting it in right. I just don't, or I have the right answer. It's just not accepting it. If a computer's asking, the computer homework is asking for x-intercepts. These are not x-intercepts. These are numbers. Intercepts are points. So I misspoke here as well. So we have x is equal to these, or actually, let's just move these down, so a bit of laziness. So then our intercepts are actually 5/3 comma 0 and negative 5 comma 0. Because those are the actual points where it crosses the x-axis. So that's our x-intercepts for this problem. Last but not least, let's do the y-intercept. The y-intercept is usually really pretty easy. This is, what's the value? I call this function h, right? Yes. So what is the value of h of 0? H of 0 equals what? Let me grab what h of x is, just so I don't have to go back and forth. And we are in the 21st century. Oops, clicked color instead of copy. And I can just copy and paste. It's gorgeous. But when h of 0 is what I care about right now. So wherever there's an x, let's make it 0 now. So h of 0 will be 3 times 0 squared plus 10 times 0, 4 times 0 squared, 21 times 0. What that's going to do is that gets destroyed, that gets destroyed, that gets destroyed, that gets destroyed. And all we're left with is negative 25 over 20. Again, because I plugged in, I went a little fast there, I plugged in 0 for x. So wherever there's an x now becomes 0. And they're all multiplying 0, so that gets turned to 0, 0, 0, 0, 0. So this is 0 plus 0 minus 25, and 0 plus 0 plus 20. This reduces to negative 5/4. So we finished this example. We have found the asymptotes, vertical asymptote, horizontal asymptote, and then we found x-intercept, y-intercept. Again, this would be the point where I actually would really recommend pausing at this point, really making sure you're understanding everything up until this point, because now we've got about 2 examples left. that will take a good amount of time. Excuse me. So I'm going to go through them slowly. We still got some time to do. Next topic. I guess I'll call it graphs of rational functions. Both when you're given information about the graph and if you're given the graph, write the function itself. Man, the tip of my Apple Pencil has been like corroded away because I use my iPad 24/7. I'm just a busy guy. And it's like eroding away the tip. And now it like will screw up what I'm trying to write sometimes. So, I'll walk you guys through an example about how to do these. Because in theory, you actually have everything in your toolkit. I've gone over everything you need to do an example like this. So let me just walk you through it. So the question is, write an equation. We're going to talk about why I'm saying an equation. For a rational function that has the following. So there's going to be a few properties, and we need to come up with an equation that satisfies all those properties. There is not the equation. We will talk about there are several ways to do this. However, there is an easiest way to do it, for sure, undeniable. That is what I will be expecting of you guys. What I am going to show is why there's an and, because it leads to another topic that I need to go over. So each of the following. Property 1. It has vertical asymptotes at x equals -5 and x equals -6. 2. Has x-intercepts at the points 2, 0 and -4, 0. Three, horizontal asymptote at y equals 8. Finding something that fits all three of these guys is a little tricky, but we have everything in our toolkits to actually figure it out, to reverse engineer it. It's almost like we've been given the function and we're told to find these. Now we're given the opposite and we want to reverse engineer it. Let's give our function a name. This comes straight from the homework. Is there, let's see, in the homework, is there a name of the function? There is not. Okay, so let's give it one. They want it to be in terms of y as your output value. That's all they say. So I'll call it f of x. F of x needs to fit these criteria. Vertical asymptotes at x equals -5 and x equals -6. What does that mean? That means that if I plug in x equals -5 and x equals -6 into this function, they will have a 0 in the denominator. So what does that mean? Let's make this f of x a little bit bigger. Well, they want it as y, so maybe I'll just leave it as y equals. And again, I've talked about the difference between when we use y versus f of x or g of x or h of x or anything like that. If you have questions about that, I've gone over it. If you have questions about it, feel free to ask via email, office hours, whatever. So if we have vertical asymptotes at x equals -5, x equals -6, that means when I plug in x equals -5 and x equals -6, I get a 0 in the denominator. I can write that in a very simple way. If the denominator is equal to this, then the bottom goes to 0. Because think about it. I'll write something quick. X equals -5 means x plus 5 is equal to 0. X equals -6 means x plus 6 is equal to 0, just by adding, in this case, adding both sides by 5, in this case, adding both sides by 6. And because of this, then therefore, x plus 5 times x plus 6 is certainly 0. In either of these cases. So that's our denominator. And we got the denominator straight from being told what the vertical asymptotes are. What about x-intercepts? Well, x-intercepts are, let's look back at the example we just did. X-intercepts are exactly when the numerator is 0. So if I'm being told that it has x-intercepts at x equals 2 and x equals -4, then that means my numerator, I'm leaving a space here on purpose, by the way. That means my numerator is going to be x minus 2, x plus 4. Because if I plug in 2, I get 0 upstairs, which means the whole thing is 0. Similarly, if I plug in -4, I get 0 here, making the whole thing 0. Now, let's pause. Let's pause for a second. Where are we? I have not expanded this thing at all. You do not have to either. You can leave it as this, x plus 5 times x plus 6. If you are so inclined to distribute and find what it will be, it'll be x squared, whatever. You can do that. We don't need to. However, we do need to know the degree of the top and the bottom. If you feel you cannot find the degree without expanding, then you will need to expand it. However, in this example, it's really not too bad. There's x to the 1 here, x to the 1 here, x to the 1 here, x to the 1 here. And when I expand, let's start with this -2. -2 times x will be -2x. -2 times 4 will be -8. So right now, at that point, here and here, all I have is -2x, meaning the degree is 1. But if I expand this guy, I will get x squared. Nothing else can make x squared. Nothing else can make anything greater than x squared. Therefore, the degree upstairs must be 2. Exact same thought process downstairs. So what that means is that the degree in the bottom is 2. The degree in the top is 2. I have a horizontal asymptote at y equals 8. So what that means is that degree 2, horizontal asymptote then, because the degrees are the same, that must mean that the horizontal asymptote is right at where the leading terms get divided. I'm trying to think. Maybe it would be simplest. I'm starting to think it might not be easy to see it. Let's do this. I have an idea. I'm kind of predicting confusion right now. It's hard to tell. Nobody's actually here telling me they're confused. I'm predicting that there might be confusion. Let's call this y prime, because it won't be the actual answer. And let's leave it like this for now. At this point, where we're at is we've satisfied 1 and 2. Now we need to make sure we satisfied 3. To do that, maybe let's expand it. Expanding this, we'll get x times 4, so it'll be x squared plus 4x. And then we'll get -2 times x, -2 times 4, will be -2x minus 8. Over. Expanding the bottom, we'll get x squared plus 6x plus 5x plus 30. Combining these two terms and these two terms, we get top is x squared plus 2x minus 8 all over x squared plus 11x plus 30. Now it's, I think, a lot easier to see that the degree up here is 2, degree up here is 2. Not only that, now that they are degrees match, we need to make sure that if I were to divide through, that I'm getting 8. Because I'm told that there's a horizontal asymptote at y equals 8. If the degrees match, the only way that can happen is if the leading terms divide to 8. And this is an example of a situation where we have an equation. Because I really can just slap an 8 there. Oh, no, I can't do that, because if I were to do that, what would happen is it would screw up the asymptotes. So, or rather the x-intercepts, I think it'll screw up. It'll screw up something. The solution that I'm looking for is, okay, so now we're at this point, I think we can all agree that degrees are 2. So if I were to now go backwards to here, let's just look here. Because if I were to do this, what I'm claiming is this is the solution. I just want to slap an 8 on the front. If I were to slap an 8 out here, this top part no longer will factor exactly into these two, which means the x-intercepts will not be 2 and -4 anymore. So I can't just plug in 8 there. However, if I plug in 8 out here, plugging in 2 still makes the whole thing go to 0. Plugging in -4 makes the whole top go to 0. So this is, by all accounts, a very, very great equation that satisfies all 3 of these conditions. Sorry for the confusion, not my best explanation of it. Feel free to ask me any questions, follow-up emails, office hours, whatever. All of the above. So, now let's go into really why I'm saying an equation. And to do that, let's go to our trusty friend Desmos, where I already have our function graphed. So this is our function. And what I want to do is, this is where the pinching really mattered. So I will do, the x-axis will go from, -50 to 50. And then the y-axis, I need gigantic. Let's do, I want -1,000 and +1,000. Cool. I wanted to capture this bottom part all the way down there. So as you can see, there's definitely an x-intercept at x equals 2. It crosses at x equals 2. And it crosses at x equals -4. That was the first condition. What else was there? There was also required vertical asymptotes at x equals -5 and x equals -6. Let's look at x equals -5 and x equals -6. There are these 2 lines. Try to follow them. You see the lines x equals -6, x equals -5, going all the way up. They just merged, kind of. Let's make it so they're still obvious. And I made the y-axis gigantic so that as I'm scrolling up, it gets closer and closer. And as you can see, we're only in the 900s. Let's expand it even further. I want 10,000. Yes. As you can see, oh, this is perfect. Look at that. X equals -5, x equals -6. The function is not touching it. If we were to zoom in really far, it will not be touching it. It's really close, but it's avoiding those asymptotes like the plague, which is exactly what we wanted. So that was the second condition. Definitely satisfies that. Let's look at the horizontal asymptote at y equals 8. For this guy, I want the opposite on Desmos. I will want the y-axis relatively small. Let's do, -100 to 100. And then I'll do, we want horizontal asymptotes, so we want gigantic x. Let's do -1,000. Let's see if 1,000 works. And then +1,000. Haha, perfect. Because you can see the line y equals 8. The function will not touch. Now, keep in mind, I'm not messing with the function at all. I'm messing with the scales. Just zooming in and out of the function. That's all I'm doing. So I'm not making magic happen here. So this function definitely satisfies everything that was described here. But it is not the only way to do it. Because if I were to very simply do another function. I'll call it y tilde, because why not? Just a different name for it. What did I end up doing? Come on. Cubes. X minus 2 cubed, x plus 4, all over x plus 5 all cubed, x plus 6. I'm basically claiming, let's do it a different color so we know it's also extremely different. We'll do it purple. Purple's my favorite color. I'm claiming this guy still satisfies all three of these conditions. If I were to plug in 2 and negative 4, the top still goes to 0. The only difference is we're going to get 0 cubed. Not much of a difference. Downstairs, exact same thing. Plugging in negative 5, plugging in negative 6 will give us 0 in the denominator. Again, plugging in negative 5 will just be negative or 0 cubed. Still 0. And if I were to draw this guy, it's going to look different, but it satisfies the exact same conditions we were just talking about. There is definitely x-intercept at x equals 2, x-intercept at x equals negative 4. There will be horizontal or vertical asymptotes at negative 5, negative 6. Let's mess with the scales to do that. I want negative 100, 100, and then negative 10,000 to 10,000. Perfect. So again, at x equal, where's the bottom? Oh, there is no bottom on this guy, that's why. At x equals negative 5 and negative 6, watch those two lines in the middle. As I increase more and more, those lines are getting closer and closer to them. Let's up the ante a bit. Let's make it go so that the y-axis goes all the way up to 1, 2, 3, 4, 5, 6, 7. Getting closer and closer to touching those lines, never actually touching them. So this function satisfies the same conditions. The only thing that changed here was I slapped an exponent here and here. Oh, I forgot to show that there's a horizontal asymptote at y equals 8. I'm sure that's believable though, because the degrees will still be the same, so we'll still get 8. These exponents get a fancy term. These exponents, there's not a great definition for it, but these exponents, maybe some of you have heard of them before, are called multiplicities. We will not dive much into multiplicities, largely because I think the best way to look at multiplicities is with more calculus. However, there is a reason I need to bring it up, and that's the last homework problem on homework 8. I would like to go over that with you guys because I think this is a really, really hard problem, and that's what this guy looks like. If you do not mess around with the multiplicities, you will never get a function that looks like this. And the question literally says, write an equation for the function graph below. So let's attack this problem. And I'm actually kind of forgetting how to do this problem, so let's start a fresh page and let's try and figure it out from the top. So what do we have? Immediately, there is a horizontal asymptote at y equals 0. What does that mean? That means upstairs, the numerator must have a smaller degree than the denominator. Doesn't tell me a whole lot, but certainly tells me enough. Also, it is telling me there is one x-intercept. 2, 0. Which means the only thing that'll make this function 0 is when x is equal to 2. So I can already tell you, let's call this function q of x. Probably wants y in the end, but whatever. That means there's a whole bunch of jargon going on. I know it's going to be a fraction. That'll be my fraction bar. And then there's a bunch of noise happening upstairs and downstairs. And my job is to figure out what that noise actually is. I know that it crosses the x-axis at 2, 0, which means the top must be of the form x minus 2. There will be some function or power here, I'll call it alpha. There will be some exponent there to it. We don't know which one yet. Let's not worry about that quite yet, though. Now, What we also know is the y-intercept is here. I don't care too much about that yet. I don't think that's going to be too helpful. What will be helpful are the vertical asymptotes, because those are what's telling me we'll be going to 0. What will happen in the denominator. So I have asymptotes exactly at x equals -3 and x equals +4, which means x plus 3 to some power times x minus 4 to some power downstairs. Now, what we want is the horizontal asymptote is going to go to 0. Cool. So that means the degree upstairs must be smaller than whatever these degrees will be, the sum of them. Cool. Also good to know. The last thing we will need, before we really dive into it, I'm just thinking now, this y-intercept is very interesting. Because that y-intercept is basically saying q of 0 will be -112 rather. Cool, we will definitely need that. So let's think for a moment. Well, let's see what happens. If I were to plug in 2 now, so this would be my q tilde, because it's not, I'm giving it a different name because it's not complete yet. I haven't finished the problem. I still need to find out if there's a leading term here and what these exponents are. So I'll call it q tilde for now. So what happens when I plug 0 in there? Well, that'll be 0 minus 2 over 0 plus 3 over 0 minus 4. So this will be -2 over -12, or 1/6. So these definitely will need powers on top of them. Definitely. Because I need this guy to be -1/12. So what powers are going to make that happen? Well, if I instead did a square here, that would make that 16. 3 times 16 would be 48. We'll get 2 over 48 or 1 over 24. Aha. So if I square both of those guys, I think I will get it. And I'll explain, if this is right, I'll explain why I got that. Yes, it will be right. Beautiful. So, I am squaring these because, let's recap. Let's recap everything. This is -12. So, I'm calling this guy q tilde of x. The reason being is because I don't know if there are going to be exponents. But I want to know I want to start to learn the behavior of this function. And this is also saying write an equation, something that'll work. Anything that'll work. But when I plug in, and I need, because the y-intercept is 0, -112, I need q of 0 to be exactly -112. But in this q tilde, which is kind of my first attempt at q, when I plug in 0, like I was saying earlier that I just erased, it would be 0 minus 2 over 0 plus 3 over 0 minus 4, which is -2 over 3 times -4, which is -2 over -12. Oops, screwing up a bit. Which would be +1/6. Not what I want. So I do need to do something. And that something is, the only thing I really have liberty of is with exponents. Now again, it's asking for an equation. Just one. So I don't need, there's a lot of ways I can go about this problem. The way I'm thinking about it though, is I need multiplicities. The way you usually think about multiplicities is, so let's look at around here. This asymptote at x equals -3 comes from this x plus 1. Again, the way to really talk about multiplicities is using more calculus, but the intuition is there. The intuition is, well, the multiplicity for this guy needs to kind of mimic what's happening in this area. Let's go back to Desmos. When I look at 1 over x, and let's fix the axes, we'll do -10 10. Y-axis will be negative 10, also to 10. This guy has this crazy 1 over x going up over here, down over here. That's the case here. It has this nonsense of, okay, this part's going up, this part's going up. So around here, I would say it kind of looks like 1 over x. Kind of. But it's that intuition is what I'm looking for right now. Similarly here, at this asymptote, this doesn't look like this. This one resembles more of this guy, except just flipped upside down, negated. That comes from this guy. So chances are I'm going to want a 2 there. Now again, this is my q tilde. So let's start constructing our q of x. So I know it's going to be x minus 2 over x plus 3, x minus 4. But again, this idea of multiplicities, this area resembles more of 1 over x squared. Oops, apologies, sorry. That was a bit too far. So I am going to want this guy squared. Now, let's check in. If I were to plug 0 into this guy, I'll call this, this will be my new q tilde. And let's get rid of this guy. This will be my new q tilde. Well, what happens here? There is certainly going to be a horizontal asymptote at y equals 0 because the degree downstairs is definitely bigger than the degree upstairs. But if I were to plug 0 into here, it'll be close, but no cigar. 0 minus 2 over 0 plus 3, 0 minus 4 squared. So we'll get negative 2 over 3 times negative 4 squared, which will be 16. This will be negative 2 over 48, or negative 1 over 24. Close to negative 1 over 12, but not quite. Well, how can I fix that? The way I can fix that is let's look at what's happening upstairs. Where did I get x minus 2 from? Well, I got x minus 2 from the fact that it crosses the x-axis at 2. But it doesn't really cross the x-axis. It, where's my guy? What's happening? Oh, can I not draw on that? That's kind of annoying. All right, well, guess we can't do that. I'll just do red pen. It doesn't cross. Okay, I can't draw on that image at all. It doesn't cross the x-axis at all. It sort of hits it and bounces off of it. Where do we know that does that? Well, if we just look at, very simply, x squared. Look, it hits the x-axis and bounces right off. So you can kind of say that at this point, it resembles a square. Again, if I've completely lost you, this is a tricky topic. Multiplicity is really bizarre, especially if 1, you're seeing it for the first time, 2, you don't have a lot of calculus under your belt. So this is a very tricky topic. I am expecting many questions, and I hope there are questions. I'm going to throw this on YouTube. Ask questions in the comments. I'll answer there. So where I'm going with this is, I think we're going to need 2 there. So that's our new q of x, q tilde of x rather. Now let's try it. Now let's try plugging 0 into this. Well, the upstairs, what we'll get is negative 2 squared, 4. Ooh, no, dang it, this still isn't right. Because we're going to get positive 112. But there's a way I can fix this. Don't worry. So this will be close, but no cigar. Still. 3 times negative 4 squared will be 16, which will be 4 over 48, or 112. Very close. Let's actually plug this guy in. Let's see. So we've got upstairs, we're going to get x minus 2 squared divided by x plus 3, x minus 4. And now, let's zoom out of that guy, or get rid of that. And let's go back to our function. Very close. it looks very similar. It's got that part to the left, and it's got that part underneath as well. It looks very close. Just this part to the right, this part that I'm kind of looking at now, I need to be flipped. How can I do that? Well, again, I need to be manipulating this function in a way that won't mess up the y-intercept, the x-intercept, or any of the asymptotes. Well, it turns out one of the ways we can do that is if I just slap a negative on the outside. Because if I slap a negative on the outside, all that's going to do is put a negative there, negative there, negative there, negative there. And that works. That'll give me my y-intercept that I need. And on top of that, interesting. Maybe the y-intercept. Did I plug it in wrong? Let's see. X minus 2 squared, x plus 3. Oh. I forgot a big thing here. That should be squared. Apologies. So this is going to look much better now. Apologies. This is actually what we were working with. This is actually our q tilde. And this is actually looking a lot more promising. It looks exactly like the function, just flipped, upside down. Sorry I didn't spot that sooner. Let me get rid of that. Looks exactly like our function just flipped. So if I slap a negative on the outside of it, the whole thing goes exactly the way I want it to. And so that'll be my final answer. Tricky problem. Very tricky. If any of you come across this problem, this is straight from the homework. You'll probably have different numbers than what I did. But this is the general idea of it. And that concludes exactly what I wanted to go over today. It seems like this was roughly a 2-hour-long video. I am very sorry for that. Hopefully, this is nothing more than just a really useful tool for you guys. Please ask questions about any of it. I will go over these problems 10 million times. I want you guys to do well. I spent a lot of time putting this together purely so that you guys can have a decent grasp of this stuff. And I hope it was helpful. And